All right, welcome to physics video 3.3, Newton's second law. So here we go. Newton's first law tells us what an object will do if the net force on an object is zero. Specifically, we know from Newton's first law that if your net force is zero, then your acceleration will be zero and your velocity, whatever it is going to be constant. All right? So if one of those is true, they're all true. From that, we were able to figure out that that also means that if your net force is not zero, then your acceleration won't be zero and the velocity will change. All right? So this then raises the question, well, if your net force isn't zero, then your acceleration isn't zero, but what is it? Okay? And so that's what Newton's second law tells us. Newton's second law tells us what an object will do if the net force is not zero. Okay? So that's what we're going to focus on here today. All right, so here's Newton's second law. It says, if you want to calculate the acceleration on an object, you're going to take the net force on that object and divide it by the mass of the object. So acceleration equals net force divided by mass. That's what Newton's second law says. All right, a lot of times in books you'll see that written this way: net force equals mass times acceleration. Both of those statements are true. Algebraically, they are the same thing. I tend to, for reasons that'll become clear after you understand it a little bit better, I tend to prefer this. So I usually write it this way. That said, algebraically, this one is probably easier to work with just because it's easier to rearrange and solve for m or a with that equation. So whatever, it's all the same thing. I'm going to focus on this equation at the beginning of the video, and we'll do one example of this one at the end. All right. So also notice up here I've written down what the units are, right? So A stands for acceleration. We're always going to use meters per second squared. Net force, any kind of force, we're always going to measure in newtons. And mass, we really haven't talked about mass in this class. You hopefully learned about it in chemistry, but mass is going to be measured in kilograms. But to be a responsible teacher, I do need to teach you a little bit about what mass is. So here we go. Let's talk about mass. In chemistry, hopefully you learned that mass is defined as something along the lines of a measure of how much matter makes up an object. All right, when you measure the mass of an object, you're basically counting particles. Okay, the more molecules or atoms or electrons and protons or teeny little particles that make up your object, the more of those particles you've got, the more mass you've got. Okay, so mass is counting matter. Okay, more matter, more mass. All right, in physics, we define mass as a measure of an object's inertia, which, to be 100% honest, I don't love that definition. I like the chemistry one better, but it introduces the idea of inertia. Okay, and what I want to make sure that you understand here is that in physics we say that all matter has inertia. Okay, and so let me explain what inertia is, and this will make a little bit more sense. All right, so inertia is an object's resistance to a change in motion. Okay, when you measure how much inertia something has, you're measuring how resistant it is to a change in its motion. A change. This word right here is colossally important. So please make sure you understand that we're talking about how hard it is to change the motion. All right, so it's probably easiest to do by way of an example. Again, in the back of your head, I want you to keep in mind this, that in physics, we're saying that an object with more mass has more inertia and vice versa. Okay, and hopefully have a good idea of what has more mass, right? It's very similar to weight. Not the same thing. We'll learn about that later on. But for now, you can kind of think of it, more mass means more weight. Okay, so why does mass measure an object's resistance to a change in motion? Why does mass measure inertia? So imagine that your right and left arms are equally strong. If you push an empty shopping cart with your left hand and a full shopping cart with your right hand, which one's going to move less? Imagine that. You got two shopping carts and you're going to push them both. Isn't the heavier one going to move less? All right, so the full one moves less because it has more mass. It has more inertia. It has more resistance to a change in motion. When you push the empty shopping cart, it's going to move because it's light. But when you push that full one, it's going to be resistant. It's going to be harder to move. Okay, the full one resists a change in motion because it has so much mass. It has a lot more inertia. Okay, if you couldn't see the shopping carts and couldn't reach your hand into the shopping carts, and I said, hey, you know, which of these two shopping carts has more mass, you can figure it out by pushing them. And the one that's harder to push is going to be the one that has more mass. Okay. Similarly, if the two shopping carts are rolling at you, the heavier one's going to be harder to stop for the same reason, right? it's got more inertia, it has more resistance to a change in motion, okay? If the empty shopping cart hits you, you're gonna go, ow, don't roll shopping carts at me. If the full one hits you, it could knock you down and really hurt you, right? Because it's harder to stop. It has more inertia, more resistance to a change in motion, okay? So that's the idea of inertia. So here's what Newton's second law says. Newton's second law says acceleration is net force over mass. So mathematically, basically what it's saying is this. If you have more net force, you're going to have more acceleration. In English, the harder you push something, the more it's going to accelerate, right? Technically, this is a little sloppy because there could be other forces. So I should say the more net force is on the object, the more it accelerates, right? And think about this. If you make the top of your fraction bigger, it's going to make your answer bigger, right? Okay. And then the flip side of it is this. When you push something, the more mass it has, the less it's going to accelerate, right? That full shopping cart, because it has a lot of mass, when you push it, it's going to accelerate less, right? It's saying that as your mass goes up, your acceleration goes down. Okay? A lot of times in textbooks, they'll write Newton's second law in words, and they'll say the acceleration of an object is directly proportional to the net force and inversely proportional to the mass of the object. Okay? That in words says what this equation tells us. Okay? So I tend to like the equation as our definition of Newton's second law. So here is Newton's second law. Write it down. Know it. It is colossally important. It is the foundation of all physics. Okay? How's that for a sweeping statement? So let's do some examples. All right? So, you know what? I should rewind for 1 second. Let me do this. Insert blank page. Boom. Okay. A Newton. What is a Newton? 1 Newton is defined as the amount of force required to take a 1 kilogram object and make it accelerate at 1 meter per second squared. So if you had a 1 kilogram object floating in outer space, just sitting there, and you wanted it to accelerate at 1 meter per second squared, you would need a force of 1 Newton. This is the definition of a Newton. Okay, it's usually written this way: 1 Newton equals 1 kilogram meter per second squared. All right. So some of you right now are going, what is he talking about? Here's really what you need to know. As long as you keep your units metric, as long as you always measure force in newtons, mass in kilograms, and acceleration in meters per second squared, then your calculations are going to work out in the units you want them to. Okay. So I guess I'll just kind of leave it at that. This does imply, too, that if you have 2 newtons, that would be enough to accelerate 2 kilograms at 1 meter per second squared, or 1 kilogram at 2 meters per second squared. So again, if I lost you there, don't stress about it. Really what you need to know is keep your units metric and everybody will be happy. Okay, so now moving on to the next example. It says find the acceleration if Roy pushes each of the boxes from rest across a frictionless floor with a given force. So I'm going to do each of these examples in a different color. So here we go. First example says you've got a 4 kilogram box. From now on, I'm going to write the mass of the box inside it. So there's your mass. This one we've got Roy pushing it forwards with 12 newtons. So our net force is going to be 12 newtons because it says that it is a frictionless floor. So we're going to find our acceleration. Acceleration is net force over mass. The net force is 12 newtons. Mass is 4 kilograms. Divide it out, and you get 3 meters per second squared. Okay, and we'll focus more on what that means in a minute. You know, it's telling you that it's going to accelerate at 3 meters per second squared. It's kind of telling you how quickly it's going to speed up. All right. Now let's take a look at part B. Part B is the exact same thing, but we're pushing with twice as much force. So intuitively, what do you think is going to happen? If you push something harder, it's going to move more, right? So let's do it. 4 kilograms. Now my force of Roy is bigger. It's 24 newtons. So my net force is 24 newtons, which means when I find my acceleration, I'm going to get 6 meters per second squared, right? Notice what happened here, you guys. We have, from here to here, twice as much net force, and as a result, we got twice as much acceleration. Oops. I wanted to write times 2 up here. Okay, so we got double the force, double the acceleration. You push it twice as hard, it moves twice as much. Okay? All right, in example C, we're going to go back to a force of 12 newtons, just like we had in example A, but now we've got a bigger box. It's a 4 kilogram box. Okay, so let's do that. Here we go. I tried to draw that box bigger and failed to deal with it. 8 kilograms. Roy is going to push it with 12 newtons. So our net force is going to be 12 newtons. Let's find our acceleration. It's net force over mass, 12 newtons, 8 kilograms. Divide it and you get 1.5 meters a second squared. That says 1.5 there. So now what we've got is this. We've got the same force, but what happened is our mass got multiplied by 2, and our acceleration got smaller, didn't it? Got divided by 2, because they're inversely proportional. Basically, this is comparing the empty shopping cart to the full shopping cart. Part A is the empty shopping cart. It gives us a pretty big acceleration. And part C is the full shopping cart. It's heavier, right? 8 kilograms, and so you get a smaller acceleration. Okay? And then part D, I'm just going to kind of plow through part D. Part D is basically saying you've got twice as much mass as part A, but also twice as much force. So your acceleration, if you figure it out, turns out to be 3 meters a second squared again. Because although you're moving twice as much mass, you've also got twice as much force to do it. Okay? So, long story short, bigger force gives a bigger acceleration, bigger mass gives a smaller acceleration. Okay? So, I think we already talked through this. Which one has the biggest acceleration is the one with the smallest mass and the biggest force. The one with the smallest acceleration is the one with the smallest force and the biggest mass. And the two that have the same acceleration is the first and last one, parts A and D. So I don't know that we need to dwell on that. Okay, so now what I want to do is I want to focus on what it means for the object to accelerate. And I think it's something you know, but I want to help you visualize it a little bit. All right, so what I want you to imagine is a 40-kilogram hockey goal sitting at rest at the center of a frictionless hockey rink. Remember, the goal in hockey, for those of you who don't know, is not attached to the ice. It just sort of, it's this metal goal that just sits there. It's not super heavy. I don't know how much they weigh, but it's this metal goal that sits there. Okay, so in this example, the goal is going to get pushed around on the ice as described in the example. So I want you to tell me what the goal is going to do at the end of each time interval described. You need to be detailed and give as much information as possible. Pretend that says as. Okay, here we go. So in A, the goal is going to be pushed forwards by Roy with a force of 80 newtons for 6 seconds. So let's make a drawing. Here's the ice. Here's the goal. We said that the goal had a mass of 40 kilograms. Here's the force of Roy pushing it forwards with 80 newtons. We know that this is happening for 6 seconds. And I haven't been focusing on the velocity. In the beginning of this problem, it is sitting at rest. So that means that our velocity is going to start at 0. Okay? So what's going to happen? Well, let's see. Our net force is 80 newtons. This is going somewhere, so bear with me here. So let's find our acceleration. The acceleration is net force over mass, 80 newtons, 40 kilograms, and you get 2 meters per second squared, right? So what does that mean? That means every second, the velocity increases by 2 meters per second. It's this. We've got 6 seconds, right? So the velocity starts at 0, and then it goes up by 2. So 1 second later, the net is going to be moving at 2 meters a second, 4 meters a second, 6 meters a second, 8 meters a second, 10 meters a second, and 12 meters per second. As long as Roy keeps pushing it, there's a net force on it that's going to cause it to keep accelerating as long as he keeps pushing it. Okay? So at the end of part A, the goal, the net, whatever it is moving at 12 meters per second. Okay? So when we move on to part B, that's where we're going to start. Okay? So at the end of part A, we're moving at 12 meters a second. So now in part B, let's draw our goal again. Roy just got it moving, right? So we know that the velocity of the goal is 12 meters a second, right? Now it says Roy lets go of the goal. So look, it's 40 kilograms. If Roy stops pushing it, there's nothing pushing it forwards. We said it's frictionless. So that's it. That's our drawing. So what's the goal going to do? Pause it. Think. All right? Nobody's pushing it. The net force is 0, right? There's no friction on the rink. Your acceleration is 0. So the velocity is going to be constant at 12 meters per second, right? It's going to keep going at 12 meters a second. Okay? I have no idea how long this video is here. I've lost my clock, so I'm going to keep going. Sorry. All right, in part C, it says Sally begins pushing the goal backwards with a force of 120 newtons. All right, so Roy is gone, but Roy's going to push it backwards. So what's going on now is this. Here's our goal. It's 40 kilograms. At the end of the previous part, the velocity was 12 meters a second. Sally's going to push it. Here's our force of Sally, negative 120 newtons. She's going to push it for 2 seconds. So let's do this. Our net force now is negative 120 newtons, right? Oh, I forgot to write down the time is 2 seconds, right? So let's find our acceleration. It's net force over mass, negative 120 newtons over 40 kilograms. Divide it out, and you get negative 3 meters per second squared. All right. So what does that mean? That means every second the velocity is going to decrease by 3. So we could either make a chart, which I guess is fine, right? Time, velocity, 0, 1, 2. The velocity begins at 12 meters a second, but then it's going to decrease by 3. So 9, 6 meters a second, right? All right, the other way you could do that, instead of making a chart and saying that it's going at 6 meters a second, is make this your VI. Let's look at what we know. We know the VI is 12 meters a second. We know our acceleration is negative 3 meters a second squared. We know the time is 2 seconds, so we can find our final velocity by plugging our numbers into that equation. So you end up getting 12 minus 6 gives you 6 meters a second. You get the same answer. Okay? So for part C, the goal is going to slow down to a rate of 6 meters per second. All right, part D, now Roy's going to push it forward 2 also with a force of 120 newtons for 8 seconds, and Sally's still pushing. So now we've just got this. I'm going to do this one pretty quickly. Roy's pushing now. He's pushing forwards with 120 newtons. Sally's still pushing back with 120 newtons. Remember, our velocity was 6 meters a second from the previous part. So what's going to happen? Well, our net force is 0, right? Which means our acceleration is 0, and the velocity is going to stay constant at 6 meters a second. Okay? I think I have 2 more screens here, so we're almost done. All right, part E. Now Sally increases her force to 140 newtons. So here we go. Let's draw this. 40 kilogram safe, or what is it, a goal. The velocity is 6 meters a second. Roy is still pushing with 120 newtons, but Sally is pushing with 140 newtons. So now, what's our net force? It's going to be negative 20 newtons, right? What if I actually show the work here? It's negative 140 newtons from Sally, plus 120 from Roy. So your net force is negative 20 newtons. Find our acceleration. It is net force over mass, negative 20 newtons, 40 kilograms. So you get negative 0.5 meters per second squared. The velocity is going to decrease now, right? Because Sally is pushing with more force than Roy is. Okay? So let's figure out what the velocity is at the end of our 10 seconds, right? So let's write down what we know. We know that the initial velocity was 6 meters a second, because that's where we left it in the last example. We know the acceleration is negative 0.5 meters a second squared. We know the time is 10 seconds, and we're looking for the final velocity, right? So VF equals VI plus AT, or you can make a chart if you want. The only problem with the chart is if your time is not a whole number of seconds, you get stuck. So when you plug in your numbers, you're going to end up with 6 minus 5 gives you 1 meter per second. So Sally has slowed the box down to only 1 meter per second. All right. So there we go. Last slide. All the examples I've done so far, we've used this equation to find the acceleration. I want to reiterate, you can also find net force. So in this example, it says, suppose you wanted to push a 6 kilogram box with an acceleration of 3 meters a second squared. How much force would you need? Well, net force is mass times acceleration. So we've got a 6 kilogram box. We wanted to accelerate it 3 meters a second squared. Multiply it all out, and you get 18 newtons. That is how much force you would need to get it moving. Please, 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 please keep in mind, this is the net force. So if it's a frictionless surface, then that's the force that you're going to need, right? That says 18. All right, so I'm not going to answer this right now because I know I'm probably already over 15 minutes. But the question I want to leave you with, how much force would you need in this example, if everything else was the same, how much force would you need if there was 12 newtons of friction? Okay, and we'll start the notes with that tomorrow, or start class with that when I see you next. Okay, so I apologize if that was long. I'm trying so hard to keep these short, you guys, but a lot of information. Okay, so I'll shut up. Have a good day. Off you go. Boom. Where's my recorder to stop it? Stop. Oh, 20 minutes.